How do you do this? You make the person breathe like this. You create a shutter over here. So he's not breathing against a shutter. Now his airflow will be diverted like this. So first there is one resistance. Next there are two resistances. You quickly make two measurements before his lung volumes can change. And by subtraction of the two measurements and division by the known resistance that you yourself added, you can get lung volume. So this became my first publication. I was an intern at this point in time. And unfortunately, it made me think publication is easy. Because this was probably this remains my only paper in which the reviewer simply wrote back, why didn't anybody else think of this before and accept it for publication immediately? And one got the wrong impression that publication is that simple in life. It has never really happened to me since. But the real important thing was this. I am very sure that this simple rearrangement of equations was obvious to almost anybody in the field who wanted to do it. There was nothing unique that I did. I just happened to be an asthmatic who was my father's guinea pig in a lab, panting against a closed shutter during an asthma attack, feeling very uncomfortable. So it was a personal problem. Because I was a medical student, I understood the papers and the physiology. And it became a simple question of wanting to find a solution and being equipped to find the solution, and perhaps looking at it in a blind spot area where the type of people who needed to look at simply hadn't bothered before. So the basic idea was there's much scope to improve upon what exists. That's a philosophy I've maintained for the entirety of my career. Even if something seems well established, there is always scope to improve upon it. And small career progression research topics can always be found if you're willing to look hard. Just a little bit new perspective would help.
Just go and oh, okay, so only we are seeing it. Just do this. And
okay. So I'll come now to this. I mean, like Rakesh said, I spent a long time doing medicine, pulmonary disease, critical care. Then I did a PhD in physiology. So 12 years later, after I was an intern, I was still in the beginning of my research career. And the problem this time that we took was whether mitochondrial dysfunction could be a connecting link between obesity, metabolic syndrome, and lung disease. Why did we pick this problem? It was very obvious by that point in time that both asthma and obesity were doing a concurrent epidemic. If you're obese, your risk of asthma went up. If you're asthma, your risk of obesity went up. And there appeared to be a link between the two. And there was some work coming out of our own lab that was suggesting that mitochondria are dysfunctional in biopsies of people with asthma. Now, this made a lot of sense. Cellular metabolism, vitality, metabolic syndrome, mitochondria are very well known. They were not very well known in lung disease. So again, that typical type of an area. There was all the evidence that mitochondria may be important. Very few people had looked at it. And because the concurrent epidemics of asthma and metabolic syndrome, each increasing each other's risks, it was likely to be a central organelle given its basic biology. And I'll not tell you too much about this part of the story. We found that a metabolite very well described in metabolic syndrome called asymmetric dimethylarginine. What asymmetric dimethylarginine does is it uncouples the nitric oxide synthesis to the point that your NOS becomes a producer of reactive oxidant species, thereby creating a huge amount of stress, inflammation. And there are a variety of ways one could go about it. One could decrease the ADMA, one could increase the eNOS, one could use statins to basically compete and bring down the ADMA degradation. You could give a lot of L-arginine. You could decrease arginase. You could give antioxidants. In a series of papers from our labs, we started the field of asymmetric dimethylarginine and asthma, obese asthma in particular. And this work did very well. And now if you look at it, you will see trials going on in human patients with obese asthma. And they're already finding that L-arginine and statins may be partially beneficial in such people. But that's not the point of the story today. The point of the story towards changing of disciplines comes from this work in which we showed that mesenchymal stem cells can donate mitochondria to dying lung epithelial cells, thereby rescuing either lung injury and preventing airway remodeling. So these are some pictures. Okay, it hasn't shifted. Maybe it's go back. Okay. It's a heavy slide. Maybe it will take a few seconds to move. Okay, no, there's something else. Let me just. Okay, yeah, this slide is important. So these are mesenchymal stem cells with red colored mitochondria. These are epithelial cells with green colored mitochondria. And you can see red colored mitochondria are actually moving to epithelial cells. This was one of the first descriptions in the world that stem cells can donate healthy mitochondria. Yes.
What do you prefer? Questions at the end?
Anytime, anytime. Yeah, so these are nanotubes. So exosomes can also do it, but so can something called tunneling nanotubes. So what you would see, you will see these nanotubes forming between the cells. And you can see mitochondria moving between them. So we have videos of actually a mesenchymal stem cell coming, forming a nanotube with a cell and transferring mitochondria.
So now, the red stain is for?
These are both mitochondria. Green are also mitochondria. These are GFP mitochondria. These are RFP mitochondria. So we basically expressed RFP in mesenchymal. So we could look at the mixing happening. And for example, these are actually, so we took GFP mitochondria of MSC, put them into intratracheal space, and you can now start seeing GFP labeled mitochondria starting to appear inside the lung tissue. Spontaneously. So the degree of transfer is greater if the recipient cell is dysfunctional and the donor cell is healthy. If the recipient cell is healthy, very small amount gets transferred. If the donor cell is dysfunctional, the transfer is much less. We haven't published that last part yet. But if you were to take MSCs from an obese mouse or a diabetic mouse, you would see much lower levels of mitochondrial transfer. And the reason this experiment was important to us, because we've been saying for years that mitochondrial dysfunction is important for asthma. But whether I give statins or L-arginine or antioxidants, there are so many possibilities, right? Now we could isolate this. We could give MSCs either capable of donating mitochondria via a protein called MIRO1 or MSCs incapable of giving mitochondria. Everything else would remain the same. Because the health of the mitochondria does not change, the machinery that moves the mitochondria to the other cell, only that machinery, and we took a basically Hail Mary pass on this one. Neurons are very long, so neurons also have to move their mitochondria. And neurons use this machinery with a protein called MIRO1 to move it. So we assumed that the same machinery would be preserved in nature, and we expected that MSC might be using the same machinery, and it worked. And without showing you all the details, we quickly came to this experiment. So this is a cockroach extract given to mice. These are proliferating airway smooth muscle and fibroblasts, the brown stain. So this is airway remodeling, right? Our expectation was that one of the reasons, so to take one step back in time, one of my biggest contributions to this paper was delaying it actually. My student came to me and said, sir, we are looking at electron microscopy of airway epithelial cells. I see lots of dysfunctional mitochondria like my lab had always seen, but a part of it is very near a fibroblast, myofibroblast technically. And the myofibroblast has healthy looking mitochondria, and the part near the myofibroblast in the epithelial cells also has good looking mitochondria, if mitochondria can be called good looking. Is it possible that the myofibroblast is donating mitochondria to the epithelial cells? And is it possible one of the reasons for these type of mesenchymal cells to start proliferating in the lung after injury is to donate mitochondria and rescue the dying cells? I thought the idea was interesting. I asked experts, and experts told me it's very unlikely. So on one side, I communicated back to him that doesn't look like a very likely idea. But on the other hand, all ideas must be pursued because experts are very often wrong. So I could either take credit for that we continued the work, or I could take the blame for the fact we took 6 months extra on it. But the fact remains, we learned in our lab that I am usually the one most likely to be wrong. So we pursued this further. And this now illustrates exactly that point. When you create cockroach allergen inflammation in the lung, you get airway remodeling with myofibroblasts. If you give mesenchymal stem cells, you can see the brown is much less. If I take MSC that have been engineered to donate even more mitochondria, you can see the brown is completely gone. And look at the last one. These are also MSC. Miro has been knocked down. They cannot donate mitochondria. Everything else is normal. There's secretion of IL-10, anti-inflammatory cytokines. Everything is normal. But yeah. So
how do you further
the transport protein? It's not the mitochondria you're changing. It is the protein required to transfer the mitochondria called Miro1 that you're increasing or reducing. If I were to change the mitochondria, the health of the MSC will change. But changing its ability to donate mitochondria, ability to rescue mitochondria. And that we showed in a huge series of experiments in both cell culture and in vivo. And basically what we find, now this is airway hyperresponsiveness. Y-axis resistance, x-axis is methacholine. So when you give methacholine to a normal mouse, which is basically sham, blue, it barely reacts. If I give it to an asthmatic mouse, here in red, it reacts. What you see is, if I give a highly mitochondrial transferring MSC, that's the yellow line, it's almost back to normal. But if I were to give an MSC incapable of donating mitochondria, that is the dashed line, nothing changes on AHR. Inflammation comes down, inflammatory cells come down, but the structural remodeling of the lung that creates AHR does not change. And that's a very important concept in asthma. You can give all the inhaled steroids you want, you can bring down inflammation as much as you want. The fundamental AHR of asthma does not go away. And importantly, AHR is a very poor predictor of inflammation. There are people with very low levels of inflammation, but very high AHR. There are people with rhinitis who have no asthma, who have very high AHR. So they are two very different things. And while I don't want to overclaim on this data, what we were able to show, what we had been saying for a long time, that mitochondrial dysfunction is a critical aspect of the asthmatic phenotype, was finally proven more by this experiment, which was very peripheral to where we were going. But ADMA then made complete sense, right? Now, if you join the two, ADMA goes up in obese and metabolic syndrome people. It creates mitochondrial dysfunction. It will basically both make the recipient bad and the donor bad. And you would end up with things that look like this, and which other people have been able to show. We never did the human studies. In India, you know that getting a bronchoscopic biopsy of a uncomplicated asthmatic is impossible. It simply cannot be done. And in the US, they are routinely doing bronchoscopic biopsy even of severe asthmatics. So pretty much all the human work proving all this came out from the US afterwards. But it was a nice time. So American Thoracic Society, 2 years ago, the theme of the ATS meeting was mitochondrial dysfunction in lung diseases. And I got to organize the preventing and treating lung disease via mitochondrial targeted therapy session in it. When we started in 2007, nobody talked about mitochondria in lung disease. Now in lung fibrosis, it's a very important topic. We had a wonderful trial started with a mitochondrial targeted therapeutic called PQQ before the COVID-19 pandemic. Unfortunately, as you can imagine, nothing happened this year, but we'll get back to it. But branching off to why other disciplines. Okay, I think it just takes time to come up. While it comes up, you will see a picture of, well, let me just wait for the picture to come. I think because the internet is a bit of a delay.
One of the needs, but there could be other ways.
Of course, but in this particular one, because Miro1 transports only one thing, mitochondria. And the only protein we have knocked down is mitochondria. Miro1 is an adapter protein that binds to mitochondria on one side and microtubules on the other side. There is nothing else that it does. So this is about as clean as it can get in molecular biology. You are knocking down the specific mitochondrial binding protein to microtubules. Nothing else it does. In fact, you can knock down Miro1 and everything will stay absolutely healthy in cell culture. Nothing will change. Of course, if you knock down Miro1 in a living organism, the brain will not develop. The neurons cannot function. They're too long. Their mitochondria need to be able to move. But for a normal cell, the cell is so small that mitochondria don't need to move from part A to part B. So this is what a typical picture of mitochondria looks like. And we could see that as we give mitotoxic agents, the shape shifts from these kind of mitochondria to these kind of mitochondria. So we refer to these as linear, donuts, and blobs. Not possibly the best names for them, but that's the name we came up with. And then we wanted to see if there was a change in the mitochondrial structures. Now, there are two ways to do this. You can ask your students to count hundreds and thousands of them over days and weeks. And that's exactly the way I was going about it. And these are just better quality pictures of what we are talking about: blobs, elongated, and donuts. Or you can hire a chemical, well, actually the chemical engineer was already there in my lab. He knew no biology. And he did not want his significant other, the biologist, to be sitting there counting mitochondria. So he decided to write a supervised learning approach in which the shape of the mitochondria would automatically be calculated by the computer. And this approach is called a random forest. Why is it called a random forest? If you train it, there is a forest of decision trees. Each decision tree is a tree. Each tree makes a vote regarding is this shape or that shape. All the trees in the beginning have random weights assigned to them. And the algorithm runs round and round given a training set until the trees develop the correct weights to process the signal and give you the correct classification. You don't do anything except figure out the right data sets. Enough examples of blobs, enough examples of elongated, enough examples of donuts. And these could be in the hundreds to 500s. You feed them in and you keep letting it run until the accuracy reaches 95, 96%. And then you have a computer program that can automatically classify a shape. The same thing can be done from letters from A to Z. The same thing can be done for chest X. It is absolutely agnostic to what it classifies. It just needs enough examples. And for very simple shapes like this one, just the curve of a blob and the fill of a blob is enough. And later on, you can get it to mark the areas it is seeing for the classification to make sure it's in the right area. So this is what it finally looks like. Let me just give it a second to catch up. I'm sorry, many of these slides are high resolution slides, so they are multi-MBs. I didn't realize there would be a problem. So
the next one comes up. Is it possible that amongst the mitochondrial diseases that we have, it is just the channel that may be affected and did not?
Yes, there are lots of mitochondrial channelopathies creating this, but those are typically heritable disorders. And of course, in asthma, that is not the situation, but there are multiple examples of channelopathies in mitochondria, giving you aberrant mitochondria, aberrant shapes, and so on. But yes, that's a different area. And we actually, on a genomic side, work on that quite a bit. So we have a pipeline called Mitomatic, in which given the general sequencing, mixed mitochondrial plus nuclear genomes, it will automatically parse the genomes and give you an output regarding which mitochondrial defects and diseases are likely. But that we do on the genomic side. Okay. Oh yeah. It's in fact even now in the market. So we standardized it a few years ago. Then we Eurofin, the company. So Eurofin licensed it from us. So now through Eurofin, you can get a Mitomatic readout on any genomics thing. So basically the Eurofin mitochondrial pipeline is ours. Because it's easiest, but if you ever want it freely for academic purposes, you can have it. There is no problem in that. So Vinod and Sridhar, who have been here before, are the right people. They developed it. But to really make it enter the market, it's easier to go with. So for neurogenetics, we have gone with Lal. For mitochondrial, we've gone with Eurofin. So you can see here now that the computer is doing the classifications. Elongated, donuts, blobs. The advantage of this approach is, and don't worry, don't look at this particular slide. It's not projecting well. We could actually do time course analysis of when ROS rises, when shapes change, when you give a particular treatment, when things are reversible, at what point things become irreversible. So using thousands and thousands of images that we had collected for that paper, we were able to write the first automated shape classification of mitochondria paper, in which we were able to figure out what may work, what are markers of poor health in mitochondria, and what are the points of transition after which it becomes irreversible. So the reason I brought it up was, while my interests had in the past been in computer science and so on, I was not doing anything with it. But with this chemical engineer coming to my lab, showing us the value of a person who brings in a completely different perspective and knows zero biology, we decided it was time, and this is about the same time this paper in the New England Journal was published, where it talked about the future of medicine and how the biggest leaps in the future would not come from the devices, but from ability to handle the data. It talked about how more complex diagnostic and prognostic categories would come, and very importantly, they will yield formulas that will be useful for clinical purposes, but defy summary in a language most of us can understand. Now, this was important. Basically, what they're saying is we will all end up using algorithms. We have no clue what they mean. And we can't even talk about it. We can't describe it. Beyond the way I spoke about the random forest tree, that there is a decision forest. In the forest, there are multiple weights. The weights are randomly assigned. Computer tunes them. In the end, I get a classification. If you ask me to explain how exactly the computer is classifying the shapes, even with this, I would be hard pressed to give you an exact answer. Imagine it is more complex than this. I would be able to give you no examples except to tell you this is my accuracy. Now, this may be unsatisfying or satisfying. I will not get into that, but that is the future of medicine. And I'll tell you now, coming back to why we use this in pulmonary function testing. Now, obviously, my PhD is in physiology. I'm very fond of PFTs, and all of you know this. This is 9/11. So many of these people doing the cleanup had significant exposure and they had respiratory complaints. 72% of them had absolutely normal spirometry. So significant clinical complaints, absolutely normal spirometry, and a huge pretest probability of having a problem. So impulse oscillometry showed that these people actually had a problem. So let's come back to what is impulse oscillometry. In impulse oscillometry, what you're doing is you're feeding in pressure waves into the lung of multiple frequencies. If I gave you a circuit with an unknown resistance and a reactance and asked you to solve it, the simplest way for you, feed in multiple voltages of different frequencies, find a resonant frequency, and start solving it. Pretty much the idea is the same. The person is breathing on this side, there's a loudspeaker on this side. Loudspeaker puts out either pseudo-random noise or time discrete oscillations or simple spikes, which are square waves, which you can solve mathematically as in a different way. So what you can do with these things is you can get a time series of measurements. Now these time series of measurements look like this. They are very noisy. So you are creating oscillations. So for example, you might be doing 6 oscillations per second. In those 6 oscillations per second, you are solving for each oscillation. On top of it, your normal breathing is going on. So everything is being mathematically separated by a simple Fourier transform. You are separating your natural breathing frequency, the changes coming in pressures and flows because of the superimposed pressure waves, and then you're solving it. It looks like this. Now, that's a normal person. That's an asthmatic person. And the average is the same. I've chosen this example for the average to be the same. So even with impulse oscillometry, what you can make out is if I was to do something simple like taking an average, you may not be able to distinguish this normal person from this asthmatic. But here is a additional transform we have done. And you cannot see it very well, but this is very small oscillations. These are large oscillations. All I did, I passed it through a filter that only transmits your breathing frequency oscillations forward. All the other oscillations are removed as noise. And the logic is your airways are sticky and inflamed in asthma. So as you breathe in and you breathe out, there might be larger changes in your resistance than in a normal person, because the airways might stick and then open again. Now, these would be too small to be measured by spirometry, but a very sensitive technique like oscillometry might be able to pick them up. And that's exactly what you see. If you could, these are large oscillations, these are small. Even if you look closely here, you will see a certain frequency of big oscillations on this side. Now, why was this important? We realized this was one parameter that by theory we could create. What if we didn't even bother to create a theory? What if we simply said, let's take every possible parameter of a time series of mathematical complexity, throw it into a random forest system, and see what comes out. And what you see is, so what random forest does is, it creates a shadow variable. That's a nonsense variable. That's the one in blue. Then it looks at all of them, then starts removing those parameters while doing the classification. Now, if you have a useless parameter, whether you keep it or you don't keep it makes no difference to your classification. If you have a good parameter, if you throw it out, your classification will drop. So all the parameters marked here in green are the ones that random forest says, if I drop them from my classification, they matter. That's your shadow variable. That's where nonsense starts. Everything on this side is probably useless. And in the end, what you can see is in a single run, and that's COPD, by the way, that's normal over here. COPD and normal is usually quite easy on spirometry, but these are 10 breaths, 10 normal breaths. The machine can classify COPD and healthy. And of course, we went one step further. We said, can we do asthmatic versus normal? Classifying a well-controlled asthmatic and distinguishing from a normal is a non-trivial problem on spirometry. They both have very similar spirometry. This is the type of ROC you get. This is probably one of my favorite slides. This parameter that we thought through a hypothesis, not through random forest, is called volume dependence. This is log of volume dependence. Everybody who's a green triangle is a normal. The red and the blue triangles are asthmatics paired samples. Blue when they are well controlled, red when they are under an asthmatic exacerbation. You can see spirometry cannot distinguish them easily. These are all mild people. This is oscillometry. You can see oscillometry does a better job, but it's not great. This is log volume dependence. You can see patterns within the time series of an oscillometry. Can distinguish even a normal asthmatic under his best control from a true normal quite easily. So this finally led, and I'll give you one more example. This is the NMR spectra of an asthmatic's exhaled breath condensate. By eyes, we can see something over here. This turned out to be ammonium. Who's going to look at all these? The classical way is you solve them for chemicals, and then you compare the chemicals, right? We asked ourselves the question. I mean, the computer doesn't really care, and we know that solution of a NMR for chemicals is non-trivial. What if we were to simply look at the entire pattern, the pattern of the entire NMR spectrum? The biggest problem is dilution. So when you try to solve for chemicals, you have to adjust for dilution, and nobody knows in this world how to adjust for dilutions between two EVC samples. Some people use urea, some people use conductivity, some people use electrolytes. Fact remains, none of them works perfectly. But water will not change the shape of the spectrum. It might make it smaller, it might make it bigger. But if you were to throw machine learning at NMR spectrum of people with asthma, you might be able to devise endotypes. What you can see is we started with random forest from a chemical engineer student in mitochondrial shapes, and now we were all over the place. And I'll show you, not spend too much time on it. I'll just wait again for it to catch up. Basically, two physician students who came into the lab to do PhDs chose to become physician data scientists. And one of them basically, important to show those people's photographs. So I'm going to wait on this side of it. But Dr. Tarpritesh Sethi, yes, he worked on the impulse oscillometry time series. Dr. Kaundinya Desi Raju, He worked on the NMR spectra of exhaled breath. Both of them became India Alliance early career fellows. He is now at IIIT Delhi, pursuing the interface of data science and medicine. And he is now at THSTI, getting ready to go to Oxford to do prediction of preterm delivery from ultrasound images collected during pregnancy. So it's a very important possible career track that I think will become more and more important in the future. I kept this slide here that there are good examples now in India of people pursuing a data science career after doing a medical degree. And this is the most recent work right now coming out of the lab with Dr. Rakesh Lodha at the All India Institute. We have a cohort of 256 children followed up every 3 months for 5 years with lung function testing at every visit along with clinical data. And we are able to show that the likelihood of an exacerbation over the next 3 months is predictable with about 80% accuracy using oscillometry and time series analysis. So this is something interesting that we'll publish soon. But you can tell the people who are starting to lose control before they lose control. And what has been shown is that every time you lose control in asthma and require oral steroid treatments, you lose a little bit of lung. It'll never come back again. And of course, there are other complications of giving steroids. It's not much. But the fact is, if you can keep people away from exacerbations, their growth and their lung function will be better over time. And that was the real purpose. And of course, there are side benefits. We are able to get money to create a new portable handheld oscillometer. It does not yet incorporate all the AI, but the device is done. FDA approval came in 2020. So now we have a handheld oscillometer that we can do to start doing these kinds of studies in the field. And of course, during COVID, we were able to use the same strength we built at IGIB to do an X-ray classification system for people. And I will never say anything is going to be specific for COVID. It's just a viral pneumonia. But it can distinguish a viral type bilateral pneumonia from a usual pneumonia from other things. It has features that make the accuracy reasonably high. And not even a human is outstanding at detecting COVID-19 on X-ray. So there are fundamental limitations of how much you can do with an X-ray. But this kind of strength is being built up by my team over the years. So I'm going to come now towards the end. There is no end innings. There is only a middle innings. I will end at my middle innings. At this point, I was an established researcher. And the problem became the bigger and fuzzier. I told you in the beginning, right? Sometimes you define gaps. Sometimes it is career progression. And sometimes you're picking a problem because it matters to everybody. And here the problem was, can we understand and improve respiratory health of Indians? Now there are no clear solution domains, right? It's public health and physiology and molecular and modeling and unknowns and intangibles. And it's classical example of biting off more than you can chew because you don't know what it is. And to first understand what are you dealing with, you need data. So we built these. We built these e-health centers that went around the country, all data coming to the cloud. By the end of this approach, we had more than 100 centers all over the place. We had more than 1 million patient visits, and then we more or less gave up on it. We gave up on it because while we were collecting a huge amount of data, it was poor quality data. And there's not much you can do with poor quality data. I mean, I use this cartoon to say that you can multiply it, you can divide it, you can do whatever. But bad data is bad data. So this approach clearly did not work out for us, although it gave us some press and publicity. It gave us an understanding of how many people come with respiratory problems. It gave us that. But you need better ways. And the better way came with Dr. Sandeep Salvi. Some of you might know him already. He used to be the director of Chest Research Foundation. And he decided to ask a very simple question. Why do people come to see doctors? And it's amazing that in all the data that we have, we can't even answer that. So this was a one-day point prevalence study. These are where our doctors came from. 8,000 of them reported on every patient they saw that day using a pre-decided very simple questionnaire where they are just every patient is a column, every organ system is a row, and you mark off what the patient is coming for. And basically with 2 lakh patients and 7,500 doctors giving you data, you had a one-day vision of why people come to see doctors. We chose it, in the old Hiranyakashipu style, neither in the summers nor in the winters, nor in this time nor in that time, to be an average day in India. And then the next problem comes is visualization. You can make bar graphs and bar graphs and bar graphs, and it will not serve the purpose that you did it for. So in molecular biology, we face this problem all the time. We have huge amounts of data that need to be captured. So this is called an alluvial graph. What we have done is a network analysis of all the different reasons why people came to see doctors, condensing them in nodes. Each node becomes an organ system. The heaviest node sinks to the bottom, drags its connections down with it. As a respiratory physician, at least as an ex-respiratory physician, at every decade of life in India, the biggest reason for people to see doctors is respiratory. This, interestingly, while you can't read it, is circulatory. Circulatory is relatively unimportant. By the fifth decade of life, fourth decade of life, and fifth, it is the second most important reason people to see doctor. Hypertension is the biggest component. That's endocrine. A decade before circulatory becomes really important, it becomes the main reason for people to come see doctors. And these nodes actually merge. I have maintained the color, but on a full network analysis, these nodes just come together. It's a large group of people coming with both circulatory and endocrine problem, classically diabetes, hypertension, and CAD. If you were to look at some interesting thing, well, it doesn't matter over here, but we could, for example, see that anemia combines with women in small cities and towns around the second decade of life, runs till the fourth decade of life, and then goes away. Obviously, menstrual anemia. We could see similar, but we could see it doesn't happen in cities. But again, that's not really the main issue.
It is interesting.
It is interesting, yes. It's not visible because it actually drags the. Yeah, it's not coming out very clearly. But you get these connections, interesting connections between anemia and women, and ages of life, and town, and cut this data by towns and cities. But here is something else where we cut it. The small towns had higher respiratory frequencies than big cities. Now, because of Sandeep's work, it has become obvious, perhaps dirty fuel, right? But here comes the problem, and that's a classical big data type of solution. When we did this study, we never asked, do you use a chula, do you use an LPG? Now, in hindsight, we can see from our data that there is much more diagnosis of airway disease and COPD coming out in small cities by percentages by the network analysis. But we had for 1 lakh people, local LPG cylinder sales data and census data on the e-government website. So we can make an assumption. You make an assumption that the patient comes from nearby. These are local doctors. These are not big tertiary towns, but tertiary hospitals. And for that area, you know the population, you know the LPG cylinder sales. So you can create an index called LPG cylinder sales per unit population. You can attach that new variable to every record, right? And then you can do what is called a Bayesian network analysis. In a Bayesian network analysis, looks like this. So if A is correlated with C, B is correlated with C, and you want to see if A acts via B to go to C, you hold B constant and vary A, given sufficient data. If A acts on C via B, then the minute you hold B constant, varying A will not change C. And this kind of thing can be done by computers at scale. This was the first time in our lab we did this work called direction graphing or Bayesian network analysis. And here is LPG cylinder per unit population. It has only 2 connections, 3 actually. Connection 1 is obstructive airway disease. Connection 2 is rhinitis. And connection 3 is whether your doctor has an MBBS degree. So that was interesting. So small town people with low LPG penetration had non-MBBS doctors, interestingly less rhinitis, but much more obstructive airway disease. And these are quantitative graphics. So I can actually go from quintile 1 to quintile 5, increasing LPG penetration. This is around 64% penetration. And I can look at expected changes in obstructive airway diseases. So it went down from around 12% to around 6%. And yes.
Is it that no, women are more affected in the small towns?
Yes, so I could split it by gender. In this particular case, women were more affected, but at least from a Bayesian graphing point of view, it was similar because even when you're a child and you're next to your mother, it's gender independent. So if your house has dirty fuel and your mother is keeping you in the kitchen or nearby as you cook and there's poor ventilation in the houses, even the male child will get affected for the future. So as a bulk association, it was cross gender. If I split it, it is stronger for women than for men. You're absolutely correct. And in Sandeep's work, it is more women, by the way. And sometimes you do find differences in the way you do analysis. Here we find a gender-specific increase in women, but significant across both genders. So I'm going to start now winding up. This made us think India has a huge amount of respiratory disease, something that we should all probably be aware of. It brought me to think about why John Hutchinson, who invented the spirometer, called vital capacity. He called it vital capacity because people with small lung volumes die fast. That's why he called it vital capacity. He suggested it as a measure of insurance evaluation. In the Framingham cohort, incidentally, the strongest risk factor for premature cardiac mortality is a low FVC. It is not cholesterol, it is low FVC. Your risk for every 10% decline in your FVC goes up by 20% for a cardiac mortality. Indians have the worst FVC and FEV1 in the world with a normal ratio. Worst, 30% lower. We are bang within the area of highly increased cardiovascular morbidity and mortality of Framinghams. The average Indian falls in that range. So we wanted to ask a very simple question. Because of our work in India, we call this normal. The word normal is a very confusing word. Normal can mean normal statistically. Normal can mean healthy. We mix the two words. If most Indians have small lungs, it does not mean that most Indians are healthy normals. It simply means it's a common finding. Here is some data from our lab. Now we have compared everybody's FVC on a global score, adjusted for age, height, gender, weight, all these things are taken care of. You are simply plotting a Z score of where they would be on a global distribution. These are markers of small airway disease, R5 minus R20 oscillometry. Like we had a portable oscillometer, so we take advantage of these things. You can see the smaller your ZFVC in absolute stone cold apparent normals. Your markers of small airway disease are much, much increased. I mean, these are strong associations. If you ask how soon does it set in, we took 2,611 children across 14 Jawahar Navodaya Vidyalaya across this country and did spirometries and oscillometries and inflammatometry, measuring inflammatory cytokines and a variety of other things on these kids. Without spending a huge time, we find that a distinct cluster of thin children, let's look at the blue, low lung function, very high levels of TNF alpha, interferon gamma, and IL-8. And then there are children who are not so thin, that's waist to height ratio. That is your Z score for FVC. That is your TNF alpha. IL-8 is almost universally increased across India based on Western values. There is no Indian value per se. And so basically what we find is inflammation, thinness, and low vital capacity is seen in 40% of Indian children at the age of adolescence. So the poor lung function of India is in my opinion, not normal. No matter what huge amount of work done in India for normal equation says, it starts very early in life when we are kids. Already in Delhi, we can start seeing South Delhi children having good lung function. They are tall, taller than their parents typically, and have good FVCs. And when you look at children from around the country, they're actually quite small and have poor lung function. And I'm adjusting for height when I say all this. So I think we have deep problems in the health of this nation from a lung point of view. If you have low adult lung vital capacity, you will get COPD by the time you are probably 60 or 70. Constant decline in lung function with a low starting point accounts for the majority of COPD in this world. It is not what we used to think. smoking causing accelerated decline of lung function. That's a very Western concept. In a global concept, low starting lung function with a constant slow decline creates more COPD than others. That's why India already has non-smoking COPD. That is why as Indians stop dying of heart disease and start living longer, we will see a huge amount of COPD. So a COPD epidemic is coming. I hope some of the work we have pointed out to mitochondrial dysfunction, inflammation is relevant towards improving the respiratory health of Indians. I think this is the real model. Obviously, small lungs don't create heart disease. It is all these factors together, including epigenetic factors. We know that children born to Indian origin parents in America have better lung function than their parents, but worse than white Americans. So it doesn't go away, but it starts getting better if you're born there. If you immigrate there at 10 years of age, it makes no difference. If you're born there, it makes a difference. And these things are important, I think, for public health. I'll end with these lessons, which are mostly from myself. Enjoy science. This is best when you are learning new things. If you don't, it gets boring. Then it becomes only career progression. And it's hard to maintain interest in career progression for all your life. Work with people who bring new perspective. And that typically means going outside your usual group. It's almost impossible to keep talking to your usual group and get new ideas. And last, as far as possible, towards a certain stage of your career, I would not advise this for a student, for example, have a larger question in mind. If you have a larger question in mind, it will force you to do the talking. So these would be my only suggestions. And I'm in a place which clearly has been very, very important in this current pandemic. COVID heroes, everybody, and thank you all. Yes, please. Yes. Yeah. So we have done that. Yes. So actually, we started historically with electron microscopy, and then moved to confocal for scale and living systems. So everything that I'm showing you in confocal was already seen in electron in 2007. That's how we got started on the area of mitochondrial dysfunction in asthma. So we were looking at biopsies of asthmatic patients and lung tissue sections of mice with allergic airway inflammation. And we saw these swollen mitochondria and broken down mitochondria on EM, but it's not a very dynamic system. So eventually we shifted to correlates on confocal, but you're absolutely right. We have done the EM.
So we generally don't observe these linear ones or as we said, it's mostly swollen or the broken down.
Yes, that's also a bit about how you fix things, but depending on which cell you look at and how you process the cells, you can still see, a maybe 3 or 4:1 ratio in normal ones, and about a 1:1 or 1.5:1 ratio in the small circular spheroid ones. And in the really bad cases, you will see absolute circles, small circles, and sometimes, but you don't see the big ones. The big ones is a bit of a confocal thing because of the way the dye spreads. Because as the mitochondria swells prior to breakdown, the dye spreads through it, giving that appearance. So you're right on that big swollen that you never see. You see small circular, you see 4:1 ratios, and you see the spheroids in the middle, ovoids in the middle.
Sir, may I have a question?
Associations. We have this doubt whether cause or effect.
Yes.
So if you have such a doubt,
Right. So which is why I thought the most important experiment was the MSC. Because MSC is absolutely causal, right? Because I am now replacing the mitochondria. Before, all the work that I showed in one slide was about nitric oxide, statins, L-arginine, variety of possibilities. So you can never get causal. But when you get that one experiment where you have MSCs capable of transferring mitochondria and not capable, everything else is identical, and you see a complete difference in phenotype, where MSCs unable to give mitochondria are unable to rescue AHR at all and prevent airway remodeling at all. While MSCs capable of giving mitochondria are completely able to reverse the phenotype. So that is a causal experiment because you have left only one variable and it is temporal. So if you look at either Hill's or anybody else's sequence of things, temporality is critical. These mice only got better after MSCs were given because you have all the other controls. The only difference in MSCs was ability to donate mitochondria. We measured the bioenergetics, we measured the proliferation, we measured the cytokine release potential. We measured all the well-known anti-inflammatory cytokines in the secretome of the mitochondria of the MSC, leaving us with only one possibility. And then there is, of course, the background of plausibility. Right? So plausibility is the work before
that. Sir, may I have a question?
Many times,
Yeah.
Yes.
will not be able to do any.
So the BOLD study has standardized everything on the NDD Easy 1. Now there's Easy 1 2, and there's an inbuilt QC. So if you were to use the QC value that comes out with every spirometry and only take ones with high QC, you will find that the operator dependence becomes almost gone for things like FEV and FEC, but will remain for mid-expiratory flows, which you cannot change. Because even the QC is determined primarily on the start of the expiration and the quick gain in slope, but nobody ever looks at the mid part. So what we tend to do is we ignore MMEF, which many 25 FEF, 25 centimeter, whatever you like to call it. We focus on the FU and FEC in these studies. The minute you go to the middle part of spirometry, operator variability is tremendous. I agree with you on that.
So when you did the study,
yeah, so we only use FEC and FEV1 and only select high QC on the same instrument in all 2,500 people, NDD Easy 1. That's how the BOLD is also being done.
Studies been done on neurons also, or there is a plan to do?
On the mitochondria?
Yes.
Yes, beautiful work. So it turns out that in the brain, the equivalent of MSC is the glia. So people showed in, and nothing to do with us, we don't work in that area. So people created infarction in mouse models. And they changed the ability of the glia to give or not give mitochondria. And they showed if glia became unable to give mitochondria, the infarct size became very big. And if the glia were healthy and capable of donating mitochondria, the infarct size became small. So the equivalent cell to MSC became the glia, and the neurons, of course, became the recipients. And the effect of mitochondrial donation in stroke models was protective of the brain. There may be other papers also, but this was one of the earliest people to cite our work and take it to the brain area. And now suddenly, if you start thinking about it, well, I didn't show you the data. So we show that if we take MSCs from diabetic mice, either old ones or diabetic ones, obese ones, let me not use diabetic, because obesity is leading to diabetes, obesity is the primary one. We find old MSC from old mice donate mitochondria, but these donated mitochondria have minimal capacity to rescue, but the donation is fine. The MSC from obese mice with metabolic syndrome, their MSC cannot donate mitochondria. And the reason also we find is calcium. So the entire Miro1 process is a calcium process. Miro1 can only bind mitochondria if calcium is low. In a healthy cell, calcium is quite low. As cells get stressed, intracellular calcium rises. So the way the transfer works is calcium is low. Miro allows the mitochondria to hop onto the microtubule. It reaches the stressed cell, calcium is high, it hops off, and it keeps going like a shuttle. So we see that high levels of ROS and high levels of calcium in MSCs of mice with metabolic syndrome seem to reduce mitochondrial donation quite a bit. Now, this is going to be important for stem cell therapies in general. But now when you start thinking of why some people will have large infarct sizes and small infarct sizes, these things may be clinically relevant, maybe. Because the ability of your glia to support your neurons may depend upon the overall metabolic status of the individual.
has very good clinical applications
Yeah, I mean, but none of it is our work. I'm kind of paraphrasing other people's work.
in each, in each system. It might be different.
Yes.
But, cardiac muscles also, we have mitochondrial diseases, mainly affect
Yes.
the brain and the heart, eyes also. So probably it has very wide ramifications and clinical implications.
So all of you must have heard about claims of MSC therapy being beneficial in cardiac disease, for example, right? Heart failure and all this. And all of you heard about huge variability. My personal opinion, now I'm getting away from hard data to opinions. I think a huge amount of this variability comes from nobody has a QC process for MSC. We showed tremendous variability based on the source of origin of MSCs and how they're handled in their ability to donate mitochondria, but not in their ability to secrete anti-inflammatory cytokines. And the markers remain the same, all the CD34, everything will remain the same. So my belief is that if we were able to come out with a way to describe high quality MSCs capable of high quality mitochondrial transfer, we would start getting a lot more uniformity in our clinical data. So my lab is working on it, how to improve it so that autologous MSCs can be used, and in heterologous MSCs, how to quantify it. Let's see if it works. So far, variability has been our enemy.
So, Anurag, the phenomenon that you described towards the end, how specific is it for the respiratory system?
Not at all.
To me, if you talk to a nephrologist, our GFRs are lower.
Yeah.
If you talk to an endocrinologist, our pancreatic reserve is lower. If you talk to possibly neurologists are the only one who are not talking about it, and we say Indians have brain problems. Okay, but for every organ, the same is true. You talk to a gastroenterologist, and we think that our absorption capacities are much lower than those in the West. It's possibly a common phenomenon. That's also reflected by the fact that if you see a relationship of body mass index with survival or mortality, in the US, as body mass index increases, the mortality increases rapidly. Whereas in the South Asian and Southeast Asian populations, increased BMI and the relationship with survival or mortality is very little. It's actually the other way around. Or should I say, basically it is a phenomenon that I use in my statistics lectures, and it depends on which part you are seeing. If you draw, grip strength versus age, it would increase with age and then will go down. And they are seeing that half of the curve and we are seeing this half of the curve. So, really speaking, do you think respiratory disease is going to increase as we live longer? So, or is it going to be every disease is going to be just much more as we live longer, as is expected?
So, let me answer that. So, the most important part of this graph is this. If phenotype, in place of ZFPC, you could put some cardiac function or renal function or something else.
And you would see the same.
I believe you would see the same. I have not measured it, so I cannot say. I believe it's part of a subclinical stunting phenotype. That would be the best way I can put it. But what is very important is it tells you this stunting phenotype is operating at scale in India, even in people who have crossed the original nutritional barrier. They're not short of calories, these people. They're getting adequate calories.
Possibly it takes 2 or 3 generations.
It is that or it is sanitation. So sanitation might be the big difference between South Delhi kids and people living outside. Again, I've not measured. So in Bangalore, there's a nice study. They looked at children of premium schools in inner city Bangalore. They went to the suburbs. They went to rural Karnataka. Beautiful decline as you go out and out from these centers. But coming to your second question, do I believe it's equally important for all areas? No. See, lungs are one of the most reproducibly declining organs in the body. One of the reasons they're almost an exterior organ, almost. Well, they are, topologically, they are exterior organs. And environmental challenges in India are massive. So given the combination that you start small, and I didn't put one slide here, I plot data from Vellore and Delhi and NCR with the x-axis being age and the y-axis being the z-score of apparently healthy people. You start at -1.2z at 10 years of age, and by the age of 60, you're at -3. So a 60 to 70 year age group profile of India is at -3 standard deviation compared to their counterparts in the rest of the world. And if you just think about exercise capacity of older Indians, it's pretty obvious what I'm saying. So because lungs, there is no good solution for them. You could, target kidney disease if you wanted to. Lungs, there are no good solutions. So I think lung disease will become clinically more important than many others. But, suffocation is a terrible problem to have. But I don't think it's anything unique to the lungs. I think it's that inflammatory phenotype occurring in a large number of Indians, programmed during the first 10 years of life, which is important. And I would say it comes down to, and I'm not advocating anything else, I would simply say it comes down to sanitation, cleanliness, public health interventions. If we don't get that right, we'll not get anything else right. So all the molecular research on one side and simple things like sanitation on one side.
Yeah, I think, yeah. Simple. Like, that's like points into NRT1, etc.
Sorry, I missed which drug?
Coenzyme Q, OQ,
okay.
and Menardion.
Yeah.
In vitro and in vivo studies in mitochondrial, there we found some use. So you don't need raw mitochondrial. But very seldom I see that they are available on market of level and so today, what's your take on the usefulness of them? Either uromitochondrial or any other?
I'll take 2 minutes to answer this question slightly longer. One of the, I removed those slides from my talk today for time. I believe that the gut contains the ancestors of the mitochondria, right? I mean, and the bacterial metabolites are heavily influencing the mitochondrial function. So there's a huge gut microbiome to mitochondrial crosstalk going on. So we mapped, if you were to do a PubMed search, type everything linked to mitochondrial dysfunction, type everything linked to microbiome. You will find a 2/3 overlap. We published this in Mitochondria a year ago. 2/3 of the diseases currently being linked to microbiome have previously been linked to mitochondrial dysfunction. So in silico, we calculated all the possible metabolites that may be coming from the gut. And we built the reaction map of the mitochondria from 400 reactions to 1700 reactions. We'll send this paper out soon. So in those 1700 metabolite reactions, we can now feed in the gut metabolite reactions and see what would allow mitochondrial function to be preserved under stress. CoQ clearly is one of the possible ways one could do it, but there's a better molecule called PQQ, pyroquinoline quinone. In 2005, it was called a mitochondrial vitamin. This mitochondrial vitamin then got removed because we still don't know what reaction it does. But we know it is critical in mitochondrial health. It's a more powerful antioxidant than PQQ. It is specifically targeted to mitochondria. It is only produced by bacteria. It is available on Amazon. In studies in my lab, and the paper again will come out, it cleans up asthma, cleans up COPD, cleans up lung fibrosis. Beautifully. Bleomycin induced lung fibrosis in mice. Treatment started 2 weeks after. It will just clean up the lung fibrosis. So we started a clinical trial of this at AIIMS last year. Well, last year now. Unfortunately, we started for COPD, we started for IPF. We only got 3 months worth of data before the trial had to be terminated because of COVID. Within 3 months, on the SGRQ in COPD, there's a beautiful trend. Almost everybody with COPD, gold 3 or 4, is starting to show SGRQ improvement about 8 points. IPF, there was no change whatsoever. It may never occur, it may have occurred longer, we don't know. We will send this paper out, but you are on the right track, I think, with the CoQ. But I think CoQ is too weak a molecule. You need a molecule like PQQ. And we will be trying to bring it out, maybe with a pharma company over this year or so. Right now, each capsule available on Amazon costs 100 rupees. It makes no sense. It's dirt cheap to manufacture. But a proper clinical trial needs to be done. I'm very happy if anybody at JIPMER would also like to work on taking this trial forward. It will be nice to make it multicentric. We already have prelim data from 53 people with COPD showing SGRQ clinically significant improvements. And let's see if we can take it forward.
Actually, there is another answer to this question besides a very scientific answer. I found in my patients that Tokyo was not helping.
Mhm.
And I did a search to find out what is the reason. Actually, I found that Tokyo is almost useless, which does not go with what the reports say.
Mhm.
So there is a study published, and I came up with this information that the companies which are providing Tokyo in India, a survey was done in which it was found that the amount of Tokyo which is claimed,
Okay.
only 0 to 30% was actually available.
Could be.
So that may be the
That could
reason
be.
that Tokyo doesn't, the commercial tablets or capsules which are available don't work.
That's
Probably that's another important
that's entirely
thing
possible.
to evaluate the usefulness of
I mean, we use sigma level CoQ. So for us, probably the purity was not an issue, but it was just a weaker one. And but you're absolutely right. I mean, weaker does not mean it should be ineffective. Then just the dose don't need to be adjusted. Because you use 10 mg to 40 mg of PQQ, you can use a gram of CoQ. So yeah, you're right. That might be the reason.
Okay, so I think we'll have to call it an end. So Anurag, thanks a lot for kindly agreeing to give this talk.
My pleasure.
Here. So sorry for revealing your first few slides.
No problem.
I had two options. I either had to start with that, or we've recently started an initiative that we're going to have a person from outside giving us a talk every month, an inspire kind of lecture series. And your name had been suggested by at least 2 departments. So I was thinking whether I should start from there. I thought I had to keep that for the end. So I think 4 things that I have takeaways from your talk. I think first is, go across your field. For good research, you need to, cross a boundary. Second is talk to others, and very often we in medicine, especially in medical institutions, not the institution that you have, very often don't talk even to another person. So I think that's important. Thirdly, is that you need to, while crossing a boundary, you still need to restrict to an area. So like you're saying, pulmonary is your field and not still crossover. Learn everything else, but use it in relation to pulmonary. And fourthly, I think have your own problems, so Indian problems, etc. So I think those are important messages, and surely what you've done is so multidisciplinary that it's very inspiring. Thanks a lot.
Thank you very much. Pleasure to be here.
Tea and coffee is just available in the 5.